Hey everyone, this is the last YouTube video in the series of differential equations. Differential equations can sometimes be called dynamical systems. The dynamical systems, as the name implies, is anything that changes with time. Okay, and so most of the things we've been doing in this course have been, whether they be solutions or populations or velocity, motion, so on. It's things that have changed with time, and they've changed as time has gone continuously from one point to another. Right? It starts at zero and may continuously go out to infinity, taking on all points in between. And then you ask questions like, what's the population? What's the amount of interest that you've earned, and that sort of thing. However, some things in life, even though they are a function of time, they don't change continuously, but instead they're discrete. So, for example, if instead of having what banks sometimes call instant interest, where you get paid for every instant that the money is in the bank, you get paid just maybe yearly or quarterly or something like that. So if you take your money out 2 weeks after a new quarter, you get paid for all the quarters, but you don't get paid for that extra 2 weeks. There are other things as well. If you think of populations, if you're talking about the population of mold or algae, you would normally measure that by taking the weight, and the weight is a continuous thing, which happens over time as this mold grows as time goes on. That was the very first thing we looked at in this course. On the other hand, if you're talking about, say, rabbits, for example, well, then rabbits tend to, I don't know what's the cycle, but they populate, give birth to new rabbits maybe once a year or a couple times a year. But anyway, it's in increments, right? So it's not like every second it's happening. It's maybe every month or every 2 months or something like that. So lots of things in life, natural things that we want to measure and play with, are modeled by discrete dynamical systems rather than continuous ones. And in general, discrete ones are harder to work with. Once you have continuity and differentiability available to you, you can make use of derivatives and all sorts of things that make it easier to work with. We have all the tools. Discrete, even though you're just talking about these particular numbers, it's kind of ironically maybe harder to work with. So that's one reason we don't work with it so much, and one reason why even with discrete things we sometimes kind of model it as a continuous thing. However, it's still fun and important to spend a little time talking about it. So that's what we're going to do in this lesson. And not only are we going to learn about discrete dynamical systems, but we're going to learn about chaos, which is a really interesting idea. I first learned about this stuff when I was in graduate school back in the late 80s, and it's really took the mathematical world by storm about then. It started a little bit sooner than that, but it's been very, very popular in the last 20 or 30 or 40 years, I guess, probably it's been. So anyway, I gave a talk on this for years and years, and I don't have that available to me now because it's part of a it's on a old merchandise, but I'll give you the gist of it in this talk. So let's begin with the cosine. And let's just take a number, let's say 0.9. And if you take the cosine of it, which I'm going to do right now, and so I'm going to go, let's see, make sure here. I'm in radian mode, so I'm going to go 0.9 and push cosine. And let's see once what happens. So I take not sorry, I take 0.9. I got to make sure this is in radian mode here, which I forgot to do. Here we go. Here we go. Okay. There we go. Okay. So you take 0.9 and you take the cosine of it, and you get 0.62. Now you take the cosine of that. So I just keep pushing the cosine button and I get 0.81. I'm doing it just to 2 decimal places, but my calculator is keeping it to about 10 different places. And now I take the cosine of that, and I get 0.68 or 69 it rounds to. I take the cosine of that, and it's going to be 0.77. Take the cosine of that, it's going to be 0.72. Take the cosine of that, it's going to be 0.75. Take the cosine of that, it's going to be 0.73. Take the cosine of that, it's going to be 0.75. Take the cosine of that, 0.73. Take the cosine of that, 0.74. Keep taking the cosine of that, rounds to 0.74, and it's going to just keep hovering closer and closer and closer to 7.4. Okay? So, what's going on here? Okay, have you ever done that with a calculator? Believe it or not, you were doing a discrete dynamical system when you did it. A dynamical system you can think of, if you want to remember what a function is something where you stick in a number and you get a number out, right? You stick in x and you get f of x. With a dynamical system, whatever comes out, you just put it right back in the function again. So you might start off with x naught, and then when you stick that in, you get f of x naught comes out, and maybe you call that your new x1. So x1 is f of x naught. Then you take f of x1 and you get your x2, and you take f of x2 and you get your x3, and you just keep whatever goes out just keeps going back in again, and you just make a whole sequence of these numbers, x4, x5, and so on, and that whole sequence is said to be the orbit. There's your first term. It's said to be the orbit of point x naught. Okay, so it's what happens when you just keep whatever you stick in, it comes out, and you just keep putting it in over and over and over again. It's called a dynamical system. Okay, so that's of course what we did with the cosine. Okay, and let's look at pictorially what we did with the cosine. By the way, this is also, before I go back to the cosine, this is what happens in nature as well. One example of nature where this happens is weather systems. If you think of the weather system, and they've gotten to be very, very good now at predicting the weather. What they basically do is they say, okay, here is today's weather. Let's call that x naught. And now what's going to happen to today's weather? What's going to act on it? It's going to be acted on by the rotation of the Earth, by the sun's warming, by the winds that come in, by various things that all act on it, and that's going to produce tomorrow's weather. And then what happens with tomorrow's weather? And maybe instead of tomorrow, one whole day, maybe it's an hour at a time, or even a minute at a time. And they say, okay, what's going to happen to the next weather then? And so they take that, they say, okay, all these things are going to act on it, and that's going to produce the following unit of times weather. And it just keeps going over and over again, and you get a weather system based on this dynamical system that the present weather keeps getting acted on by these various phenomena. Okay, so these things happen in nature as well as in mathematics. So let's go back to the cosine. Here's the cosine graph. It looks something like this. If I just take the portion from 0 to pi over 2, of course it starts at 1. So I'm going to do this. I'm going to draw the unit box, which is 1, 1 right here. And then I'm going to draw the line y equal x, which goes right up the middle, y equal x. Okay, so what did I do? I started with 0.9, and so here's 0.9 right here. And if I take the cosine of 0.9, I get 0.62. So now I can go over here and find 0.62 and stick that into my cosine and get the next one, which is 0.81. Then I can go over here and find 0.81 and find the next one. But that's the advantage of this line y equal x. Instead of going and finding it on the x-axis, all I have to do is go straight over, and now my y value, of course, becomes the x value. So there's your 0.62 right there. So that I can just go right there, and there's my 0.81. And of course this is a rough draft, so I'm going to cheat a little bit to just make it act the way it should act. I stick that in and I get 0.69. Here's 0.69. So here's my 0.81 right there. I find the cosine of that and I get 0.69. What happens when I take the cosine of that? I go over and there's your 0.77. What happens when I take the cosine of that? There's your 0.72. What happens when I take the cosine of that? There's your x value. There's your 0.75. And now you have a picture which describes what's going on here. How interesting is that? Boy, isn't that neat? So this is called a cobweb for obvious reasons. And you see that this cobweb is going to converge to this point right there, which is a fixed point. Something that we've been talking about a lot in this course. A fixed point is one that when you stick it into the function, it doesn't change, right? A fixed point here was a point where you put in this value of x and y, and the x doesn't move and the y doesn't move. So that was the fixed point where both of these things didn't move at all. Okay, it doesn't where the function doesn't move it. And the same thing here. Notice all of these points, you stick them into the function and you get another point out. That point right there, you stick it in and you get the same value out again. It's the fixed point. And so this orbit is converging to this fixed point. Okay, it's converging to that fixed point. So that's the behavior of this particular dynamical system. And notice no matter what point we would have started with, we would have gotten that similar behavior. I started with 0.9, but no matter where we would have started, it would have ended up doing the same thing, converging right there. Notice we have another, well, that's it. Okay, very good. So that's all I want to say about that. Okay, so as I say, these dynamical systems occur in nature, and here's one that is very interesting both from a natural point of view and from a mathematical point of view. F of x is equal to ax times 1 minus x, and this is where a is some number between 0 and 4. Okay? First of all, that should look familiar to you for a couple reasons. It should look familiar with you from a pre-calculus reason. It's a parabola. It's a parabola that goes through 0 and 1. And when a is equal to 4, it goes up to the height of 1. You can check that out by looking at the vertex. For values less than 4, it's going to be a parabola that doesn't go up so high. But the maximum height it's ever going to hit is going to be 1 when a happens to be 4. The other reason this might look familiar to you is that it's similar to the kinds of things that, again, we've seen throughout the course, where we said, how does this thing change? When did we see things like this? We had this just recently again, where we said what? This was the logistic growth of some population where you have exponential growth early on, but then you get what? You get a carrying capacity of beta, and so it's going to level out. So notice that this is very similar. You can think of 1 as being your carrying capacity, and this a as being kind of your rate of growth. Okay, so this thing right here is a discrete analog to this logistic growth, to this population thing. So you can kind of think of it, if you want to, you can think of it as the population of some organism where it goes in discrete steps, like, as I say, like rabbits that maybe have rabbits every year or something like that, rather than mold or algae which grow continuously. Okay, so anyway, let's analyze this. Okay, we'll do it the same way we did the previous one. So first of all, if you have, I'm gonna, and again, this is what I have a whole video that has this stuff that is not available, so I'm just having to draw pictures of it, okay? But here's your line y equal x right here. Here's your, I guess I'm going all the way up to here, so that's okay. Make my box like this. Okay, that wasn't quite right. Let's draw it again. Not bad. Okay, so here's the point 1, here's the point 0. And so if A happens to be, and I've got the numbers down, if A happens to be 0.4, then you're going to have something that looks like that. And what's going to happen? You start off with a value, take f of it, then what's the new value? You cobweb over, there's f of the new one, there's f of the new one, there's f of the new one. You're going to get a sequence of points that's just going to converge right down there to 0. 0 is your fixed point. Okay, so you can think of this as being like a fish population where the fish aren't reproducing enough or whatever, and so the population just dies down to 0 over a span of time. Okay, what if we raise it to 1.4 instead? Okay, that's going to raise this thing up higher. So now it's going to be something kind of like this, real roughly. So if you start at a particular point, let's see if I can make that look a little bit better. Something like that. So what happens? You start right here, it goes there, it goes there, it heads right down to that point. Or if you start here, what happens? You go there, it cobwebs up. You always just keep going until you hit the graph again, and it cobwebs up. So there, in this case, if you start with 1.4, I actually have this down, it converges to roughly the 0.29. Okay, right there is about the 0.29. That's where it converges. Okay, so you can think of that as like a fish population that converges to a steady state where that's your long-term population. What happens if we have 2.4 instead? Okay. Now this thing is going to be maybe more like that. And now it's going to have a similar sort of behavior. It's going to converge up, or it's going to converge down, and it's going to converge to 0.58 is what it converges to. Okay. What happens if we go to 3.4? Bear with me here. Things are going to get interesting pretty fast. Okay, so 3.4, that's going to raise it something like this. I'll go up even a little higher than that, I think. Something like that, very roughly. Okay. And what happens here, interestingly enough, and this is all something that you can do with your own calculator. If you have some programming ability and you can program a computer or whatever not Minitab, but MATLAB or whatever, or even Excel to do something like this, go ahead and do it, and you will put in values and just do it over and over and over again. In fact, Excel, I guess, would work pretty easily. And here's what happens: you start here, you go like so. You go there, and what's going to happen is it might move around at first, but eventually it's going to just keep oscillating between two values over and over again. These are called points of period 2. Okay, so instead of settling down to a fixed point, it bounces between 2 points. It bounces between 0.45 and 0.84. Okay? What's really interesting is that this sort of behavior is seen in nature. And this is one of the important things that's been discovered over the last 30 or 40 years. That in the past, when scientists and mathematicians have seen some kind of exotic behavior like this, where a population might bounce back and forth between two things, they always assumed that it was due to some factor that they weren't taking into account. There was some underlying factor that was causing it, but their simple model They never assumed that their simple model would have predicted that kind of behavior. But as this stuff has shown us now, as we've dug into this in the last 30 or 40 years, we realize that just simple behavior, just parabolic behavior like this, quadratic behavior, can lead to this sort of interesting behavior that we see in nature. Okay, let me make sure that you're still with me. Where the population bounces back and forth. Okay, so I'm not going to go too much further in here, but here's what is really cool. If I were to raise this to 3.5, turns out, then it bounces between 4 periodic points. It's going to bounce back and forth and have 4 points that it just jumps between. And every time you iterate, it's going to eventually hit one of those 4 points and then just keep going back between those 4 again. If that's at 3.5. So this is A, and this is the number of points. If you have 3.55, and again, check this out if you want, then it bounces between 8 of them. If you have and of course I had to choose these carefully, 5, 6, 8, then it bounces between 16 of them. And if you have any mathematical blood in you at all, you're seeing a progression here. We're doubling each time. We started with 2, 3 point, what was the original one I had here? 3.4 led to 2 of them. Okay, and so there they all are. Then, lo and behold, if you go all the way down to 3.84, I think it is what it is, yes, 3.84, it bounces between 3 of them. And here is the amazing thing with that number 3. A mathematician by the name of James York, back in, I think it was 1971, might have been 73, somewhere in there, he wrote a paper in which he proved that if you have a dynamical system which have points of period 3, because these 3 points here, they'll bounce back and forth between those 3 points. If you have points of period 3, you will also have at least some points for every other positive number. 127? Yes. There are points here where if you start right here and just iterate it 127 times, you're going to be right back to where you started. And those other 127 points also have period 127 because they're part of the loop. 29,216. Yep. There is some place where if you start at just the right spot and iterate that many times, you get right back to where it started. A really amazing thing. And he entitled his paper, Period 3 Implies Chaos. And that's where the word chaos first became used in relation to mathematics. Because basically he was kind of his way of saying you get all this strange, interesting behavior that comes when you have this kind of behavior here. Okay? So those are those different periods. Here's what else happens. For lots of other numbers, including 4, and so again, if you just put 4 into this function right here, first of all, it's never going to settle down. Okay, well, first of all, the picture is going to look like this. It's going to go all the way up to here and then back down again. Okay, so everything that comes out, you can put it back into the function. That's why it can't go any higher than 4, because whatever comes out of it, you need to be able to put it back in, and our domain is from 0 to 1. Okay, so anyway, if you take 4 and you put basically any number in there and just keep iterating it over and over and over again, it'll never settle down. Okay, not at all. But here's what is kind of amazing about what happens with 4. I think I can erase that now. If not, I'll just draw it again. If you take this thing with 4 and you put in just 2 numbers, I have 2 that I always used, 0.6 and 0.61. I don't have them all down with me. I'm kind of making this talk one where it's interactive. I'm expecting you to fill in the details. And you plug the 0.6 into this, and you do it about a dozen times, and you put 0.61 in there and do it a dozen times. I should have done this particular part. You will notice after only about 5 or 6 iterations that these two numbers are totally different from each other. Even though you started very, very close together, after only 5 or 6 iterations, they are totally different from each other. You could have just as well started with anything. And this idea that by starting close together, but that you end up very, very far apart, totally different, is called sensitive dependence. Sensitive dependence on initial conditions. Okay? And this is another, maybe the key idea behind chaos, chaotic dynamical systems. It's that by starting very close together, being just slightly off, that you're going to get totally different kinds of behavior. And here's one book, I'll show you right here, by James Gleick, called Chaos, Making a New Science. If you ever want to read a fun math book, which reads like a novel, this is the one to read. You'll learn all sorts of stuff here, and he basically shows all the human drama involved in mathematics, where you have people who went out on a limb because they realized that nature was not acting the way they were expecting. The most important example of this is with weather systems. They had these models for weather systems, and they put all this information into the computer. Here's all this information. They put all that into the computer, and they get all these results out. The next day, they took all this information and put it back in again, and they basically put it in twice. Well, once they just let it keep running again, and the other time they took all these numbers and put them in again. When they took all the numbers, they took them maybe to 5 or 6 decimal places, but didn't go out to 10. And it turns out that they got totally different weather predictions just because of the fact that they had truncated them at 5 or 6 rather than going all the way out to 10. Just by starting over again and having to truncate them, they ended up, the model gave totally different predictions. And that's why we now say that the weather system is an example of a chaotic dynamical system. It has chaos. And so the term that you often hear is called butterfly effect. And there's truth to this, okay? That if a butterfly were to flap its wings at just the right point and at just the right time, say in Australia, that it could change things that would ripple through and could totally change the weather system in North America a week or 10 days later. Okay, that's the sensitivity. It would maybe have to be a bigger butterfly, but the point is, just very small changes can give rise to totally different outcomes. The example I like of this is if ever you're going down a rapid river, and you've got these rapids, and you want to either go one way or another way, and you're going through these rapids, and the river splits off like this. And if you know anything about kayaking or canoeing in rapids, especially in high rapids, you know that there are particular times when just by giving a little touch to it, you're going to put yourself in an eddy which goes this way, and you're going to end up there. Whereas if you hadn't given yourself that little tiny touch, you're going to go on this side of a rock, whatever, and you're going to end up there. So you're going to end up at two totally different places, depending on whether you happen to put your paddle in the water at that one particular spot or not. Okay, I have a Christmas card that I let me find it in a second. A Christmas card. That I showed years ago. Here it is. It's called Contributing to Chaos. And this was a river up in the Canadian Rockies, where they told us that this went right along the Continental Divide. And so that's supposed to be a picture of me peeing in the river. I can't remember whether it was or not. That's with my back to it there. Where I was saying I'm contributing to chaos, because depending on which side I pee on, it's either going to go to the Atlantic Ocean or to the Pacific Ocean. Okay, but the Continental Divide is an example of SDIC, right? If you're standing on the Continental Divide and spit one way, it's going to go to the Atlantic, and you spit another way, it's going to go to the Pacific. Another example of sensitive dependence is in, I think it's Ben Franklin's poem. The poem goes like this. For want of a nail, a shoe was lost. He's talking about a horseshoe now. For want of a nail, a shoe was lost. For want of a shoe, the horse was lost. For want of the horse, the rider was lost. For want of the rider, the battle was lost. For want of the battle, the kingdom was lost. Okay, so you can imagine a blacksmith who's one nail short and say, okay, I'll send this horse into battle anyway. And that shoe comes off, and maybe the horse, maybe the rider would have been important in that particular battle. And so the whole battle changes, the whole kingdom changes, all because of this one bad nail, okay, or lack of a nail. So there are lots of examples like that in modern literature, so on, right, where they show things that change greatly just because of a small effect. But that's all called SDIC. Okay, see if there's any others that come from that. I guess the straw on the camel's back is another example of that, right? You have a camel and you put a bale of straw on it and it walks across the desert. But if you put one extra straw on there, that's the one that breaks the camel's back and it flops down and that's it. So that's the idea. Okay, so that's all kind of neat stuff that comes with chaos. And then here's another neat thing that comes with chaos. I can't show you all of it again because I don't have the material with me. But if you take the same idea and you apply it to the complex plane, you put complex numbers into, I'll use Z for complex numbers, into basically the complex parabola, then here's what happens. That's your new function now, okay? There's your new function. You put a number in and you get a number out. That number, you stick it back in again, you get a number out. You put a number in, you get a number out, and you're going to get the orbit of that particular number. You have a question to ask about that orbit. Does that orbit stay bounded? Do all the numbers coming out of it stay small? Or do those numbers eventually go off to infinity, just become unbounded? Okay? So that's the question to ask. And if you ask that question, and if you draw all the points black for which the orbit stays bounded, and you color the other points depending on how long it takes the orbit to go off to infinity, you get what's called the Mandelbrot set. Here it is right there. It's certainly the most complicated, in some ways beautiful object in all of mathematics. And here's the coolest thing about it. Here's the Mandelbrot set. If you take just a small portion of that, and a tiny little portion right there, and blow it up, you're going to get this right here. You take a tiny little portion of that, just a tiny little portion right there, and blow that up, you get this. You take a little portion of this and blow that up, you get this. You take a tiny portion of that and blow it up, you get the bottom part again. Okay? You keep doing that, and you keep blowing up. And so by the time you've blown this thing up 1,000,000 times, notice that you get another tiny little Mandelbrot set. That's after 1,000,000 magnifications, I believe it is. Okay? So just an incredible complex object. And any object, either in nature or in mathematics, that when you... And so this was produced through dynamical systems, through discrete dynamical systems. So any object, either in nature or in mathematics, that when you blow it up, if you basically get it to look self-similar, so that when you blow it up, the little part of it kind of looks like the original, that's called a fractal. Okay, so fractals, the way we produce them in mathematics is through these discrete dynamical systems, and so you can get them in mathematics, but you also can get them in nature. And where do they occur in nature? If you look at the limbs of a tree, Okay, here's tree limbs, things like this. And so they all kind of branch off like this. And so a small little branch has kind of the same general structure as the whole thing. If you look at your circulatory system, okay, here's the big aorta coming out of your heart, and then you get arteries that come off of that, and arteries that come off of that, and then smaller and smaller ones, and eventually we call them capillaries, and then of course they come back in veins. These things here is basically a fractal, because each one is kind of like a small portion of the entire thing. It just reproduces itself at more and more levels. And what's cool is that the body uses that in order to get the blood to the whole body. How about the inside of your intestine? In your intestine, your small intestine is meant to absorb food, but you need a lot of area in there to absorb the food, because it just through osmosis gets soaked into the cell walls, into the body. So you need lots of area for it to soak in, just like a radiator needs lots of area. And so what your body does is it makes more area by having these little finger-like things that come out from the cell wall. Not that big, but that's the idea. They're called villi. And then on those villi, you have little millivilli, and on those you have little microvilli. And so you have all these tiny little finger-like things, which I read once that if you took all those and cut them and laid them flat, all those villi, your whole intestinal wall, and all those villi, if you lay them flat, you'd have the area of a tennis court. So you have the area of a tennis court inside your small intestine that all comes from these fractal-like things. Mountain ranges are basically fractals, because they're kind of rugged at various portions, and then you come up close and it's rugged again. Okay, coastline is an example of a fractal, because a coastline looks smooth if you have a big map, or I shouldn't say it looks smooth. It has some jagged ins and outs. But now you take a portion of that, which does look smooth on the big map, and you go to a county map or a state map, and you look at it, and it's going to be all jagged again. And you take a portion of that map, which looks smooth, and you actually walk along it, and it's going to be all jagged again. So it continues to be jagged as you multiply it, as you keep magnifying it to different levels. Okay? And this is why Mandelbrot said this. He said, he first quoted Galileo. And he said, clouds are not spheres, mountains are not cones, coastlines are not lines, and bark is not smooth. Nor does lightning travel in a straight line. Nature exhibits not simply a higher degree, but an altogether different level of complexity. Okay? So he first quoted Galileo. He said Galileo is quoted as saying, nature is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures. So Galileo is saying, here's what a tree is. A tree is like this, and a mountain is like this, and whatever, a cow is like this. Okay, there's a joke about the spherical cow. So Mandelbrot is saying, no. You really shouldn't imagine and think of and study nature as being just a cylinder and circles and triangles and cones and things like that. It's a whole different level of complexity. And so Mandelbrot is a person who, as much as anyone, brought this whole study of fractals and dynamical systems into our modern life. Okay, so that's interesting, and that's what you'd expect, right? Because, as I say, if you have dynamical systems in nature, in mathematics you have dynamical systems, and they give rise to fractals. And so in the real world, in the world of nature, you also have dynamical systems, so you'd expect that you would find fractals there as well. And sure enough, we do. So we find them in trees and in clouds and in coastline and all sorts of things. Dynamical systems, whether in mathematics or in nature, give rise to these fractals. And finally, they also are used in art, okay? Because basically, Hollywood and whoever wants to take time for such things can produce nice realistic scenery just by using fractals. So this is basically taking a grid and putting different points on the grid of different heights from 1 to -1, and then you boil that down into smaller squares, and you put all points on that between 1 and 1/10, and you boil that down into smaller squares and put heights on that from 1 to 100th, and you add up all those heights, and you just keep doing it at smaller and smaller levels and add up all those heights, and you end up with really neat, very natural types of things like this. And it makes you realize, oh yeah, this is the way nature actually works. Let me show you a couple more. Oh, there's the Mandelbrot set again. Okay, so that's one of the baby Mandelbrot sets in the middle of the mama. Okay, there's another cool one. Okay, I think I've got a couple more here. These are all very neat. This is a 19. When did this come out? 1991. So this has been out a while. Look at this. Oops. Let me make sure you're back here with me again. Okay, look at that. Isn't that cool? So that's all done with fractals. There's one more. There's another one. Kind of cool, huh? So all done with fractals. So that's just a quick overview of discrete dynamical systems. Okay, so they're helpful in understanding things in nature which that change discretely rather than continuously, and they're also helpful in understanding our world. That sure enough, we have this sensitive dependence on initial conditions that is really all around us, and there's a poem by Robert Frost. It goes, 2 roads diverged in a yellow wood. Sorry I could not travel both. Being one traveler, long I stood and looked down one as far as I could to where it bent in the undergrowth. Then took the other equally fair, but having perhaps the better say, for it was grassy and wanted wear. But as for that, the passing there had worn them really about the same. And both that morning equally lay in leaves no step had trodden black. Well, I kept the first for another day, yet knowing how way leads on to way, I doubted that I should ever come back. Oh, I shall be telling this with a sigh, some day, ages and ages hence. 2 roads diverged in a wood, and I took the one less traveled by, and that has made all the difference. Thank you.